next up is the CEO of Curity, Travis Spencer. Curity was also kind enough to have our most recent course released on API authentication, which released today. And from here, I'll hand it off to Travis. Thanks,
All
Travis.
right. Thank you so much, Corey. And great to be with you all. Great to be a part of this event, and very happy to share the knowledge that we have in this area, both in this conference and in the presentations or lectures that Corey mentioned there at the top of the hour. And I'll have some more information about that at the end. But what I want to talk to you about today is API authentication and give you an overview of that and some advice. For those of you who don't know who Curity is, we're an identity and access management security company, helping you to identify and authenticate your users so that you can deploy and keep safe your APIs. So let's go on to the next slide here. Have a very short agenda, which will consist of these two parts. First, I'll talk about authenticating to the API, like just the caller or the client of that API. And then in the second part, I'll talk about how we can authenticate the user and then turn around and authenticate the client to the API so that we know both the user of an application and the caller of the API. Okay, so with API authentication, we have lots of different options. This is some of them. I think there probably are a few others, but we have basic authentication, we have digest authentication, we have something called mutual TLS, token-based authentication, and then a variant of that called sender-constrained token-based authentication, which I'll describe to you toward the end of my talk. So in basic authentication, which is defined by RFC 7617, the client is authenticating to an HTTP server. And RFCs are from the IETF, the folks that give us standards for defining SSL and TLS and all those sort of things, and HTTP itself. And in basic authentication, the client will, if it calls without a credential that is valid, it will get a 401 HTTP response code, and it will be told that that is an unauthorized request. And the caller will receive a www authenticate header, response header, that will include like a token, like a word that says the methods of authentication that the API, or more generally the HTTP server, supports. So basic is what is shown here, and that it includes this realm, and then the realm is sort of like the security realm, or the area that the client is authenticating to. And so then what the client is supposed to do is then respond with an authorization request header. And it's supposed to, again, use that word basic to signal to the server that the client is authenticating with basic authentication, because as you'll see, there's other kinds. And then it includes the password or the secret in a base64 encoded string. So it's actually clear text, but you just have to base64 decode it, and then you'll see the password of the client, or the server will do that decoding and see that. There's also something called digest authentication, and digest authentication is defined in another RFC from the same standard body, and that's 7616. And when a client isn't authenticated, it will respond again with a 401 unauthorized request, but this time the www authenticate header will include the digest token, and it will include the realm that is being authenticated to, and it will include some information so that the client can create a proper hash proving its identity to the HTTP server. And then at the end of that, which maybe hopefully you can see in that text, it says opaque, and then that's a one-time nonce, or one-time random string that the client is supposed to sign with its private key. So the response then is, using a private key or a secret, it will sign that challenge and send it back to the server, and the server will have a copy of that symmetric key, a copy of that shared secret, and will recompute the hash over that opaque value and see that it matches what is stored by the server. And if it does, then the client is authenticated. So that was a lot of time to explain a protocol that you shouldn't use. And the reason that you shouldn't use it are a few, but mostly it's just not a protocol that is used these days, and it's not really scalable in that it requires the challenge to always be sent back from the server to the client. It is good that it protects against replay protection, but there's just better ways of doing it. So you shouldn't use digest, and you probably shouldn't use basic either, by the way. Other common methods for authenticating the client to the API are things like NTLM, which stands for New Technology Land Manager, which new technology is in like Windows NT, so that should tell you something. It's basically like a binding of Kerberos onto HTTP, and it's a Windows thing. I think these days some other browsers support it besides just Internet Explorer and stuff, but in general, it's not really an interoperable or internet standard. You have AWS signatures where it will sign different parts of a message to prove the identity of the client to the server, and then a standards-based version of this, which is HTTP message signing, and that is defined in a brand new RFC called 9421. And so that is actually something to look into if some of the other techniques I described in this presentation aren't suitable for your use case. It is nascent though, so you might not find support in clients and servers just yet. There's also transport level security or transport layer security or TLS, and this is defined in another RFC 8446. And so usually in TLS, like when we use our browsers to go to websites, the only entity that is authenticated is the HTTP server. So if we use TLS with an API, the only thing being authenticated is the API itself. And so in one-way TLS, the API would have a private key, and that private key would be signed by some sort of trusted intermediary, like a intermediary that the client application trusts, a certificate authority. And so then the client knows who the API is, but the thing about TLS is that the API doesn't know who the client is, which is what we're talking about here. So what we need instead is what's called mutual TLS or MTLS. So in this case, both the API and the client have a key, like a private key, and their public key is signed by a certificate authority. So a certificate is really just a public key with a bunch of metadata around it and a signature by digital signature created by some sort of intermediary that others trust. So in my picture here, I've shown it the same certificate authority. It doesn't have to be that way, of course. You could have the API trust one certificate authority and the client trust another, and they have certificates signed by each of those authorities. But in any case, there has to be some intermediary, some broker of trust of both of these keys. And then the API will be authenticated to the client, and the client will be authenticated to the API. And so we have mutual TLS. There's drawbacks and issues with this where you need a point-to-point connection. You need to have an intermediary that you trust. It works at the transport layer. So before the HTTP message is set up, which means that you have to use lower level frameworks and toolkits to help you with that. You can't just use an HTTP client, although most do support TLS. And so that's mutual TLS, and we'll get to that a little bit more when we start talking about sender constrained tokens. So this is a way to authenticate a client to an API. Because the client has to do work, like it's an active client, it's usually going to be like a mobile app or some sort of server-based client where it can keep that key secret. It's not going to be like a web browser or an SPA or something like that. Let's talk a little bit now about authenticating the user and then authenticating the client to the API. And we do that with another RFC, 6749, which is called OAuth 2, which is a framework for doing authorization of resources to different users. So the way that works, we have these different actors here, like a user who has content at some sort of protected resource or some sort of API. And that user wants to delegate their rights to that data to some sort of application. And this application could be a mobile app, it could be a web app, but in any case, the user wants to allow the app to consume that resource, to call that API on behalf of the user. So the app needs to get access to that API, and in order to do that, it will interact with an authorization server, an AS, that will help it to receive a delegation from the user. In other words, it will get help from the authorization server for the user to delegate their rights to that resource, that API, to the application, so the application can call the API on behalf of that user. There's a lot of different message exchange patterns or flows defined in the OAuth framework, and then the whole canon associated with OAuth. There's, without exaggerating, at least a dozen different flows. One of the most common ones that I'll just use to introduce you to the whole idea is something called OAuth code flow. And the way that the OAuth code flow works is we have those different actors that we just talked about, and the user will use the application, mobile app, web app, to make an HTTP request to the authorized endpoint of the authorization server. So it's just a GET request. And on this, it has some different query parameters. And those query parameters tell the authorization server, this is the message exchange pattern that I want to do with you, because there's, as I said, many of them. So the authorization server implements the command pattern and knows from the response type, okay, this client is trying to interact with me in this way. So in order to do the code flow, I need to identify and authenticate the user. So it will use some sort of authentication service. Maybe it's external, maybe it's built in, doesn't much matter. The OAuth specification doesn't define how to do that, just says the user has to be authenticated. So this authorization or authentication service will prompt the user in some sort of fashion. Could be with a passkey, using a password, smart card, social account, whatever. And after the user authenticates and identifies themselves, the authorization server will do a redirect back to the registered callback URI of the client. And so on this callback, it will include a request parameter, which is a code, like a one-time usage code. And that code is meant to be sent to another endpoint of the authorization server called the token endpoint. And it will post this one-time usage code to the authorization server to glue that first request that happened to the authorized endpoint to this request. And this request is authenticating the client. So in the first one, we went and got authorized by the user, and they delegated their rights to the client. Now the client gets that code that represents that delegation, authenticates to the authorization server, and identifies the client itself. And then the response to that is some sort of token, a tokenized representation of the calling application, the user who was authenticated, and the rights of the user that were delegated to this client. So this access token is a pretty short-lived token that will give it access at the API, and it has a scope, kind of like we saw in the digest and basic authentication options, where it sort of says the extent of authorization of this token. And because the token is so short-lived, the authorization server might also issue a refresh token, which is a longer-lived token that will allow the client to perpetuate its access to this protected resource without involving the user again in an interactive manner. But in any case, it has the access token, and the access token will be used to call the API. The API will be able to verify that token by hook or by crook, and consume or make an authorization decision on whether or not that resource should be consumed by that client for this user. Make sense? I hope so. So another thing that I want to talk through a little bit, and we go into in the course that was mentioned at the top of this talk, is something called sender constrained tokens. So the tokens that we just talked about there, where we saw this access token here isn't necessarily tied to this application. So if this application were to give that token to some other application or some other entity, how would the API know that the caller of that isn't the original one that got the token? So what we want to do is we want to constrain the token just to the calling application that was authenticated and identified and authorized by the user to access their resources on their behalf. So the token needs to be tied to the one to whom it was issued, and the way that we do that is by using a private key that only that client has, and requiring a proof of possession of that private key every time a token is presented. So we can do this in a couple of different ways. We can do this using mutual TLS, which we talked about, and also something called Depop, which is yet another RFC. And this will prevent token exfiltration and also token sharing. So if you have a mobile app or web app and you have access tokens in those and they go missing somehow or are stolen or shared around, you wouldn't want the API wouldn't want those stolen or shared tokens to be calling and gaining access to the shared resources in some cases. So we can use sender constrained tokens to avoid that. So in that case, we would be using mutual TLS, and we would bind the token to the client who has that private key. And once we do that, then every time the API is called with the same private key that is used to set up that mutual TLS tunnel, we know that the token that's presented inside of that tunnel is the same client. So a lot more to say on that, and that's part of the reason that we worked with APIsec University to create a course on that, so that you can get all these details in a lot longer and better explanation than I've provided here for you. So here's a QR code that you could scan and take it to the course. It's a few different parts, and you'll get your API authentication certification after you finish that up. So that's all I have for you today. I hope that it was informative, and you can also check out Curity.io's website, and you'll find a lot more resources, videos, code samples, and things related to all of this and more on that website.
All right, great talk. Thanks so much. We did have a couple questions come in. And so there's the first one, what alternatives are there beyond the BFF pattern for SPA applications that secrets are not stored in the browser?
The BFF pattern is the best way to protect an SPA using modern technology. It's the only one that you probably should do.
Great. Next question. I know OAuth is promoting Depop and FAPI 2.0. API specs are looking at adoption, but any thoughts on RFC 7800 for token constraining?
Let's see what 7,000.
Yeah, if you had that ready to go off the top of your head, I wouldn't have been surprised, and I would have been really impressed.
So if I recall correctly, proof of possession key semantics for JOTS, which is what that RFC is, it was sort of a framework for saying how to do proof of possession in general, and was used and referenced from others like Depop. Back when this one was making its way through the working group, there were quite a few different ideas on how to do proof of possession. And all of those ideas kind of, I wouldn't say were abandoned, but they were proven not to be the best way forward. And so what the industry and the community coalesced around was Depop and mutual TLS, and there really aren't alternatives to that right now. So 7800 is not an alternative.
Next question that just came in, are there specific API design patterns or best practices for endpoint development that can significantly reduce remote code execution risks?
Remote code execution risks.
Yeah, I feel like this one goes a bit beyond.
I mean, with the BFF pattern, I mean, remote code execution, that sounds more like I'm getting some sort of code installed on a laptop or something.
Yeah, it'd be a lack of input handling from the users, and so if they submitted a request as a valid or invalid user, and they were able to inject system code and run that from there.
Yeah, and you want to get the app then to execute some response from an API. I would say maybe not the most common exploit. So maybe rephrase the question, but I'm not sure.
That's all right. And then let me see if I can share. Well, actually, if you want to put up the slide one more time so that everyone knows how to access the API authentication course, newest
Sure.
course over at APIsec University that just released today. And in that course, there's an introduction to API authentication, the OAuth factors, OAuth 2.0, tokens, scopes and claims, and then APIs and gateways. Great looking new course. Definitely check it out when you have a chance. One more question. Any thoughts on token binding on MTLS versus Depop?
Yeah, token binding was dead on arrival. It was never going to be implemented in the browsers. There was no support for it in other HTTP clients like OpenSSL and other toolkits like Boring. So it was dead on arrival, and I have not seen or heard anyone looking back. So it's Depop or mutual TLS, I'm afraid to say. And the thing about Depop that we found is that the clock synchronization can be a real drag. So the best way to deploy that in real life is to use the challenge that was added late in the specification.
Great.
All right.
I think that's
Great.
all we
Thanks,
have.
Corey. It was great to be with you, and thanks for hosting us. And I hope everyone will check out the website and the course, and have a great rest of the conference, everyone.
Thanks so much, Travis.
All right. Bye for now.